Hi, good evening. Welcome to today's lecture, which is again as the last lecture on credit risk. The last lecture was more like an introduction to credit risk, so defining all the important quantities that we need. And the main thing you will see today is the first proper model that is called a Merton model that allows you to understand credit risk in a structural way. And before I start talking about this, just a reminder, you might have seen it. I've uploaded a second home assignment. No worries, you don't have to submit until this Sunday, but until next Sunday. It should be is it 22nd of March, right? So let's just check before I say something wrong in the lecture. Yeah, 22nd of March. This means you have the whole Sunday. You can submit until Sunday night next week, 22nd of March. If there are any questions, formulations are unclear, or I don't know, then just let me know. Please ask before you submit, not on later after submission. Just take note that I think there's one question which you are only able to solve after the next lecture. So don't worry if you don't understand what you should do. You should be able to solve all of them after this lecture, apart from one. I think it's the last question, which you are only able to solve with the knowledge of the next lecture. So don't worry, don't panic. That's okay. You can wait until the next lecture. So this is the one on hazard rates and intensities. Good. So let's start with today's lecture. So before we talk about, the main topic of today, which will be the Merton model, the structural model, we want to finish what we have started in the last lecture, which is talking about like basic quantities and how to calculate credit risk without having a proper model. And the last thing that belongs to this category would be to talk about the credit value at risk. So this is what we do in the beginning, and then we switch over to as I mentioned, to the Merton model, which is something called a firm value model or a structural model of credit risk. And then in the very end, you see the parentheses. This means just something, not really important for the exam and so on. So this is some additional topic, which is a modification of the Merton model called the KMV model. And this is something interesting because this is relevant for practice, right? So the Merton model is the theoretical foundation. This is how mathematically, theoretically you derive things and so on. But if you want to apply this to proper data, the Merton model has a couple of drawbacks, as you will see. And what you will apply typically in companies and so on is a vendor model that is called the KMV model. So I want to talk a bit about that. So details are not too important, but that you have seen it at least once, how the things are actually applied in practice. Good. So let's start talking about the value at risk. You know what the value at risk is. So the value at risk measures is a risk measure, and measuring something like some kind of worst case loss. So it's always a number specifying the loss that will not be exceeded with a certain percentage, right? So that's the definition of the value at risk. And the credit value at risk, so be careful. It's not just the value at risk of credit risk losses, but the value at risk minus the expected loss. So this means, this is very nicely illustrated here in this picture. So here, it is a normal distribution. So we assume here for this picture that the loss follows a normal distribution. The expected loss would be 0. So expected loss is here. The value at risk loss would be, this famous number, 2.33 or something like that. And then what you do in order to compute the credit value at risk would be just to compute the difference between value at risk and expected loss, right? So in this case, it doesn't make a difference because the expected loss is 0, right? But actually, you're just considering the green colored area, the green shaded area here. So everything exceeding the expected loss. So the idea is that someone managing credit risk is taking care of the expected loss anyway. So he needs to allocate capital to the expected loss. It's just some kind of decomposition. And everything that comes on top of the expected loss is measuring this kind of unexpected loss that is measured exactly in this case by the thing that is called the credit value at risk. So it's just some notation, some convention used in credit risk. So when we are talking about the credit value at risk, we are not talking about the value at risk, but about the value at risk minus the expected loss. Okay, and I mean, we are here not considering valuation of derivatives or anything like that. So this means the loss distribution that is important for the computation of the value at risk is always the distribution under the measure P, under the historical physical measure P. Okay, just one simple example. So it's very simple. So we are assuming independence and so on. So it's just to illustrate how it works. So we have a portfolio consisting of 3 loans here. And the borrowers are not the same. So it's a heterogeneous consideration here. So we have 3 of them, different exposures, different PDs. So you see obligor 3 has a PD of 10%, which is quite a lot. We assume here, just to illustrate the calculation, that the exposures are constant. So there's no randomness in the exposure at default. Same for the LGD, for the loss given default, which is here assumed to be 50%. And here, this is what I explained in the last lecture. But this just means if you want to emphasize this, that the loss given default is constant, you could write LGD equals ELGD, in this case 50%. This means we get 50% of the exposure back in a case of a default. And then really, just for simplicity, we assume that the defaults are independent. So whether obligor 1 defaults is completely independent of a default of obligor 2 or obligor 3 and vice versa. So there's no correlation structure between the defaults. Very unrealistic, but just to illustrate the calculation here. Okay, and what we want to do actually is we want to do the same kind of calculation that we have done in the lecture when we were talking about value at risk. So we want to compute actually the credit value at risk, and I mean the approach that you have seen is always to first compute the CDF, right? This means the portfolio loss distribution, which allows you then to determine the quantiles and therefore the value at risk as well. Okay, so we want to compute the portfolio loss distribution. I mean, then you can also compute the expected loss and the unexpected portfolio loss, which means here the credit value at risk. Yeah, so don't be confused by this notation. So here, CVAR does not mean conditional value at risk. So that's a bit ambiguous, right? Conditional value at risk sometimes is the expected shortfall. That's not what we mean here. It's really the credit value at risk when we talk about CVAR here. Okay. Good. So this should always be clear out of context, actually. Good. And the calculation just has the purpose to compute first the loss distribution and then use the loss distribution in order to, determine the value at risk. Notation is here simply PDI. So the index I here, it's a super index, not a sub index. So it's a new notation. It's not referring to time or anything. So the I is really referring to the obligor. So I is in either 1, 2, or 3. Again, this is not a time, but really just an enumeration of the borrowers we have. And so what we do is we just look at the different events that lead to losses. So one possible event would be that there is no default. Then the next event would be there's a default of obligor 1. The next one would be one of obligor 2, one of obligor 3, and then you can combine them and so on. So you have a couple of different events that you want to consider separately. So the first one is really no default at all. And no default just means you look at the probability of no default of obligor 1. So this means no default of obligor 1, probability 1 minus PD1, and the second one would be no default of obligor 2, and here no default of obligor 3. And here you see why we have assumed independence, because this allows us simply to compute this probability. Otherwise, you can also do the calculations when you assume a certain dependence structure. For example, you can assume copulars and so on, but I don't want to make the calculations too complicated here, so just assume independence. Again, I want to emphasize this is rather unrealistic. Good, so we multiply the probabilities only because of independence, and we get this number here, almost 83%. And then you looked at the next event, which would be a default only of obligor 1. And this means if only obligor 1 defaults, this just means obligor 2 does not default and obligor 3 also does not default. So you can compute the probability simply by multiplying PD1 with 1 minus PD2 times 1 minus PD3. Right? This means here is a default of obligor 1. Right? And here, again, 1 minus PD2, same as in the line above, means no default of obligor 2, and 1 minus PD3 means no default of obligor 3. Okay, and then you continue in the same way. So I want to save you these calculations, not very exciting. I think you understand the principle. And then if you perform the calculations, you get the probabilities that you see here in column 3. So the first one would be the default scenario that corresponds to no default of any of the obligors. Then the first one would be the scenario where obligor 1 defaults. This means the loss is 25. Why 25? Because we have assumed an exposure of $50 and the loss given default is 50%. So we lose 50% of $50, right? That's the loss in this scenario. And then you can also compute the CDF. So remember the lecture on calculation of the value at risk. What we actually want to do is to determine the CDF of the loss distribution. This means we are summing up the corresponding marginal probabilities. And then we go through all the different scenarios. So the last scenario would be a default of all the obligors. So this means you need to multiply the corresponding PDs, sum up the exposures, multiply with 50%, and then you get a loss of 50% of 270, 270 being the sum of the exposures. And the probability is very small here, and this is the corresponding loss distribution. Okay. We start with the simple thing, which is to compute the expected loss. The expected loss can be computed in 2 different ways. So we could just look at at this table of the loss distribution and sum over the product of losses with probability. And this is the definition of the expected value. And if you do this, then you get a value of $9.5. The other calculation is much easier, but this is really to look at everything on a scenario level. So just go through the different possibilities, different scenarios that might happen. So there are 8 of them. Or you could just look at everything from a portfolio level. Portfolio level means you have 3 different borrowers. And this is the formula we have seen in the last lecture. I can just sum up, because everything is linear, the corresponding losses of the 3 obligors. This means we have a loss given default, which is the same for all the obligors. So you can write it in front of the sum. And then we have probability of the default for the first obligor of 2% times the corresponding exposure of 50, and the same for the other obligors. So this will also lead to the same number, of course, $9.5. And the unexpected loss, again, can be computed in the same way, same idea, same principle, in 2 different ways. So either you go through the different scenarios, so everything on from a perspective of scenarios, so on a scenario level. This leads to number 21.85. So just squaring the difference between the loss in a specific scenario and the expected loss that we have computed, which is 9.5, times the corresponding probability, then sum it up and take the square root. Or you could apply the formula that we have seen in the last lecture on the very last slide, where you remember there was also the component on the correlations. And here we have that the correlation between di, dj. So this is the default indicator. What is it? It's 1 if I is j and 0 otherwise. So this means there's no default correlation between different obligors. That's exactly the assumption of independence. And then the formula just simplifies to what we see here. If you compare this with the slides from the last lecture. So this is what you see here is PD1 times 1 minus PD1. So this was the variance of the default indicator 1 times the correlation, which is 1, times what we have here, 50 is the exposure at default of the first obligor squared, and so on. And then you sum over over all the obligors. So what we do here is on an obligor level. Okay. And what we actually want to do is to compute the value at risk. Okay, and let's say we want to compute this on a 99% level. And here, we have a discrete distribution. So what we need to do is we just look at the last column and check at which point we exceed the 99% level. And this happens already in the 4th row. Here, you see this, right? This is the first time we exceed the 99%. So this means the corresponding value at risk loss is what you see here. Yeah, so this is always the methodology. Look at the first xi that is exceeding, such that the CDF is exceeding the corresponding confidence level. And then the loss that corresponds to this value is exactly the value at risk. With 60 in this case, we directly infer that this number is the value at risk. This is not the credit value at risk, because in order to, according to the definition of the credit value at risk, what we need to do is to subtract the expected loss. We have computed it's 9.5, and then in the end we get, just 60 minus 9.5, which is 50.5. Okay. So what we see here, this is a bit counterintuitive definition maybe of the credit value at risk. This is something which is sometimes also called the economic capital of a portfolio. And this is exactly the same decomposition. So value at risk minus expected loss, which corresponds to, again, to the unexpected losses. And for example, with the number that you see sometimes in credit risk as a confidence level, which is 99.98%, a really high confidence level. And then this correspondingly means that the capital, the economic capital that is computed in this way, can cover unexpected losses. So all the losses exceeding the expected loss in exactly 9,998 cases out of 10,000. And if we measure in years, this means 9,998 years out of 10,000. So in almost all of the years, apart from 2, we have enough capital to cover unexpected losses. And again, this is just another name for the credit value at risk. And now the question is, why are we actually doing this? And there are a couple of stories to explain this. And this is, the main motivation would be something that is called total risk capital. And there's a decomposition of this into exactly these 2 parts that we have. So there's expected loss and one part for unexpected loss. And then you could just call this this decomposition total risk capital. And one part is there to absorb unexpected losses. And for this, we can use the, for example, credit value at risk. You could also use, of course, another risk measure beyond the expected loss. You could also use expected shortfall. But typically, I mean, if you just take the value at risk, which is still the standard measure for credit risk, then you're taking for unexpected losses just the credit value at risk. And the capital reserves, so this is the first component. If you look at this decomposition that you see here at the bottom of the slide, the capital reserves correspond to the expected losses. Economic capital, again, this is the thing we have seen on the previous slide, corresponds to value at risk minus expected loss, and then you see the decomposition on the right-hand side just corresponds to value at risk, right? Because the expected loss just cancels out, so the value at risk is actually what we want to compute, and then there's just this artificial decomposition in capital reserves, which you need to put aside anyway, so to say. There's no way that you should not cover the expected losses at least. These are capital reserves, and beyond the capital reserves, you need some additional capital for, everything that exceeds expected losses. So that's the story that is typically told. Might be counterintuitive, but you just have to take it as it is. This is the risk decomposition being used in credit risk. Okay. So this is so to say, the conclusion of what we have started in the last lecture. And now I want to start something new based on all these definitions, which is to talk about firm value models. Okay, and to give an overview, what we are talking about, there are basically two major approaches in credit risk. So the first one is what I want to talk about today. These are structural models. And in these models, what you do is you look at the asset value of a company, and you set up some model for the asset value, some stochastic process. And if I talk about a stochastic process, what you typically have in mind as an example would be a Black-Scholes model, geometric Brownian motion, or something like that. And this is exactly the approach you will see today. There are, of course, you know this, extensions of geometric Brownian motions and so on. But the standard approach is really using a geometric Brownian motion. And this explains things very nicely because you get explicit formulas, you can compute things, and so on. And then what you do is once you have the asset value that is being modeled via a stochastic process, you look at the relation between assets and debts. Assets and liabilities. We have talked a bit about this already in one of the earlier lectures. And the basic idea is that you default when your assets are, the size of your assets is too small so that you cannot cover all of your liabilities. Then you go into default. And this is exactly how default is modeled in these structural models. So this means what really matters is the relation between asset and liability side. So that's why we call this a structural model. You look at the structure of a company, at the balance sheet, actually, of a company. So this is one possible approach on a very high level. And the other one would be, instead of looking at the structure of a company, you directly look at default. So in the first approach, the structural approach, you don't model a default directly. You just say, okay, the default is implied whenever the structure between assets and liabilities is too bad in a certain sense, and then there will be a default. In the second approach, you don't look at the structure, but you directly try to model the default somehow stochastically. So you set up a model for the default. So these are the two approaches. And how you would do this in a second approach, which is called a reduced form model. So you reduce the view towards really the default. Just model this as a random variable. And then, you can also model this as a stochastic process. And then whenever there's a default, there's something like a jump in the stochastic process indicating the corresponding default. Okay, and this stochastic process that is, having the jumps corresponding to the defaults, they can be modeled in a very simple way, a very complex way that may be influenced by certain things. For example, the economic environment and so on, or only the time. So this is something we will talk about in the next lecture. So today we only talk about the first approach, the structural models, and the reduced form models is something we will consider in the next lecture. Good. Yeah, and the most famous model that in the class of firm value models is called the Merton model, so named after this guy, whose face you might have seen before. So it's also one of the inventors of the Black-Scholes Merton model. And he invented, or he was the first one proposing the model we are talking about today. And the basic idea of this model is, so to say, that we are looking at the equity value of a company. And as you will see in a second, the equity value of a company can be viewed as a call option on the debt. And this allows you, if you model the asset value via geometric Brownian motion, to compute the price of equity. Because you know how to price a call option if you model the asset value with a geometric Brownian motion, because then you can just apply the Black-Scholes formula, so to say. So you have a nice formula for everything, and this allows you to compute things. So that's, on a very high level, you will see the details in a second, no worry. That's what his idea was. He had this nice model, the Black-Scholes model, and he actually just applied it to credit risk. Okay, and so this means if you do this, then you have the stock price. The stock price is corresponding to equity. The stock price can be computed as a call option price, and this allows you to give a forecast, because this actually indicates when this depends on the stochastic process that is driving the randomness, that is driving the default. This gives you a forecast in terms of default probabilities on potential future defaults. Okay, that's on a very high level, probably very hard to process what the Merton model is about. And here are the assumptions that we need to impose before we start formalizing things. Good. So we have some stochastic process denoted by Vt, and this is modeling the asset value of the company. Okay, and this Vt will be later some geometric Brownian motion. I will specify this later, but this is the assumption that we have some asset value. So the size of all the assets, the value of all the assets together is modeled by some stochastic process. So of course it will change in the future, how the value will develop, and we just assume, okay, this happens in a stochastic way, and the standard model will be a geometric Brownian motion. And then we have this very simplified structure. There are two classes of securities. So we are looking at the balance sheet actually. There's equity and debt. And then there are some additional assumptions that are just simplifying the model. So of course, you could think of extending all of them, but for now, we're just assuming that, for example, stocks don't pay any dividends, equity does not receive any dividends, and the size of the debt is static. This means over the whole time that we consider, there's no change in the size of the debt, in the size of the liabilities. In the value, there can be a change, of course, but the size of the debt actually stays constant. So they cannot issue new bonds, new debts, something like that. It's not possible in this model. This is highly unrealistic, but I mean, it's just a simplification that allows you to compute things. And the debt, I mean, is just modeled in the standard way. This means we have a zero coupon bond. No coupons are being paid, nothing like that. Face value is B. So that's the second quantity that you need to remember. So the first one is VT, the second one is B. That's denoting the size of the debt. Maturity is T. Okay, there are no transaction costs, no taxes, and nothing like that. And all we are looking at is this one maturity, T. So what we want to make the default depending on is really whether the assets are high enough to pay back the debt at maturity T. So we are only looking at time T at what happens. So what happens in between doesn't matter for this consideration. That's the assumption here. So we are only looking at time T what happens. I mean, this corresponds a bit to the assumption that we have a zero coupon bond, and all that matters is that we can pay back the debt that corresponds to the issuance of the zero coupon bond. Well, these are the assumptions. That's the model we are looking at. Okay. And then in the next step, we are looking really at the structure of the company. So what we have is, again, the simplified view of a balance sheet. You know, there are assets, there are liabilities, so debt, there's equity, and I mean, the size of assets is the same as the size of liabilities plus equity. So that's something you already have seen in one of the earlier lectures. This means if we denote the value of equity of the stock by ST, the value of the assets by VT, and debt by BT at time T all, then VT, which is assets, so the left-hand side of the balance sheet is the same as equity plus liabilities or debt. Okay, and we are always looking at the values at time T. So that's the basic balance sheet equation we start with. And then remember the assumptions that I just mentioned. We have a zero coupon bond. We are only looking at what happens at time capital T. Okay, and at capital T, actually there are only two possibilities, right? So either we are able to pay back our debt or not. Okay, the first scenario is the good one. So this means simply that, you know, if you look at the right-hand side of the balance sheet, that the size of the assets is large enough so that the size VT is still larger than the liabilities. So losses are absorbed by equity. So this means if assets are not large enough, then equity shrinks to a value smaller than zero, or shrinks to zero, and it's, you know, the next step would be that liabilities are not large enough, which corresponds to a default. So these are the two cases. Okay, let's start with the first case. VT is larger than B. This means this is the good case. Assets are still larger than B, which is the size of the zero coupon bond. Then what happens is simply that you pay back your debt. Debt holders receive the full amount. So BT is B. This is simply what it means. The value of the zero coupon bond at time T corresponds to the full size of the nominal. Debt holders receive the full amount. Shareholders get what is left. So this corresponds to, you know, the size of the equity here. Okay, so this means according to the balance sheet equation, what is left is simply VT minus B. So exactly the size of this blue quantity here, VT, the size of the assets. I subtract the size of the liabilities, which is B. And this is what shareholders receive. So there's still something left for the shareholders. There's still positive equity value. Okay, the second scenario means that the assets are not large enough to pay back the debt. This means you're not able to pay back your liabilities. This means the company cannot fulfill the obligation, and there will be a default. This means all that is left in the company, which is less than the liabilities, is being paid to the debt holders. So they don't receive the full amount, but they just receive what is left. And what is left is exactly the size of the assets. This means in the second case, we have BT equals VT. But this means there's nothing left for the shareholders in that scenario. This means ST is 0. This means really that in the case of default, this makes sense, the stock value goes to 0, and what is left in the company goes to the debt holders, which is not the full size of B. So this means in this case, just to be clear, BT would be smaller or equal than B, and typically is smaller than B. Okay, so these are the two scenarios, and I mean, nothing else can happen. Either we are larger than B or smaller than B. And then we are looking again at these two cases from the point of view of the values of equity and debt. Okay, let's start with equity. So equity corresponds to ST. And ST, in the first scenario, the good scenario, there's no default, would be just the difference between assets and debt at time t, which is VT minus B, which is positive in the first scenario, because there's money left for the shareholders. In the second scenario, when there's a default, there's nothing left for the shareholders, so it would be 0. This means in scenario 1, it's VT minus B. In scenario 2, VT minus B is 0, and shareholders don't receive anything. So you get always the larger of VT minus B and 0, which I could also write using the positive part function, and just corresponds, now you see it, right, to the value or the payoff at time t of a call option written on assets with strike corresponding to the debt value. Okay, that's how you can just reformulate the value of equity at time t as a value of a call option written on the assets. Now, if you look at debt, it's very similar. You can also formulate this as another mathematical function. In this case, you start looking at the minimum of two values. So in the good scenario, debt holders get back the full nominal, B. So this is scenario 1. In the second case, they get less. In the second case, they get only VT. Which in the first case is larger than B. So this means they get what in both scenarios, whatever is smaller, VT or B. So it's the minimum of VT and B. And again, the second scenario, this corresponds to VT. In the first scenario, this corresponds to B. And now you can reformulate the minimum simply by writing this as B minus the positive part of B minus VT. And this, of course, is the payoff of a put option of the strike B. I mean, you see this just, okay. I mean, if B is larger or equal than, if B is larger than VT, which is the case in scenario 2, then you just get VT. Yeah, right? So this is VT in scenario 2, which means if B is larger than VT. And this is B if B is smaller or equal than VT. In that case, the things just cancel out. In the second case, the positive part function is 0. In the first case, just the two things cancel out so that Vt remains. Okay, so you can really write this in this way. So this means the equity value can be understood as a call option, where the underlying value is just the asset value. In the second case, this can be understood as B, which is the value of the bond itself, minus the value of a put option, again, on the asset value, with the strike being the value of the nominal of the debt. Okay, so we have this very nice representation, and this is really the most important, trick, or the most important relation that is being used in the Merton model to understand equity and debt simply as an important structural relation to assets, and in particular as the payoffs of certain kinds of easy to price, easy to understand options. Good, so we understand equity and debt, and the next step would be to model everything using a geometric Brownian motion. This means we have the asset value, and we want to model this using a model that corresponds to the Black-Scholes model, which is exactly the one we see here, geometric Brownian motion. So this means you've seen this equation already a lot of times. So it's just the basic equation for geometric Brownian motion involving some quantity, some constants for drift, mu v. This corresponds to the asset value. Therefore, the subindex v, and sigma v, which is the corresponding volatility for the asset value. And we have the Brownian motion, standard Brownian motion, Wt. Good, and then you know what to do, right? There's a solution, there's a closed form solution for the geometric Brownian motion, so we can write down how the asset value at time t looks like. It has a log normal distribution, and in particular, if we take the logarithm, we get a normal distribution. This is exactly what log normal distribution means. Okay, you have seen these quantities already a couple of times, just a repetition of the model we are using here. So again, what we are doing is to model the asset value explicitly, and keep in mind we model we have derived the structural equations for equity and debt value, being call options and put options respectively, on Vt. And now we model Vt with this geometric Brownian motion. Geometric Brownian motion is the model that is also used in the Black-Scholes model. And in the Black-Scholes model, you know how to compute the value of a call option. So this means using this model, we can now, in the next step, derive the value of equity based on this model. Okay, so the idea is really to use exactly what we have derived. So we have derived that St is Vt minus B, the positive part of that. So it's the value of a call option on the asset value of strike B. And because we model Vt as geometric Brownian motion, we can compute the value of equity at an earlier time, small t. How can we do that? We just apply what you have learned in last semester, how to price derivatives on stock values that are being modeled by a geometric Brownian motion. You can apply risk-neutral pricing theory. So actually all you need to do is to compute the conditional expected value under the measure Q, risk-neutral measure. And then you've learned that this equation has a solution in the Black-Scholes model, which is called the Black-Scholes formula. So this means what we get is that St can be written as what you see here on the right-hand side, which is the value of a call option on Vt with strike B. Okay, so this is very nice. So what we get really is this equation here. And just as a repetition, the right-hand side depends on certain quantities. And most importantly, I mean, the dt1, dt2, you have seen these quantities before. And keep in mind that it does not depend on the drift, right? It does not depend on mu v, but it does depend on the volatility, of course. And this is not the volatility of the equity, not the volatility of the stock that you observe, but the volatility of the asset. But that will impose a problem, because if you want to derive the parameter, right, you cannot just look at stock prices and then apply some estimation methods for the volatility, because what you would get is sigma s, not sigma v. This is not the same thing. So what we really need here is some volatility for the asset. And this, we will solve this problem later, but keep this in mind. So we have some equation for ST, but on the right-hand side, everything depends on the volatility of the assets. Okay, and then we can play the same game for the debt value. Debt value was being modeled. So I repeat the equation. So BT was B minus the value of a put option on VT, strike B. And this means if you want to compute the price of this at some time smaller t, you can do the same thing. We model VT with a geometric Brownian motion. So therefore, we compute the conditional expected value of the whole thing. So this is what we do in the first line. And then, I mean, you see that the first part, the first summand, which is just the discounted value of B, is deterministic. So we can write it in front of the expected value. Nothing happens. And the second part is just the value of a put option. And the value of put option, I mean, it also has an explicit formula. You can, I mean, there are different ways to derive this. For example, you could apply put call parity to the call option formula or something like that. So there are explicit formulas for the put option for the in the Black-Scholes model, and this is what you get, what you see here in the second line. And then in the next step, we just use the relation that, you know, you have here the n of minus d2. This is the same as 1 minus n of dt2. Because the normal distribution is symmetric, right? You can just use this relation to simplify the formula you get. Because then you get rid of the discounted value of b with this 1 minus term here, and you get what is standing here on the last line. Okay, so this is an explicit formula for BT. Yeah, and just the remark here is don't be confused here by what we are considering here. So the BT here, this is of course correct that we discount everything at the risk-free rate. We are not looking at the discounted value of B, right? So what we are doing here is you can really look at BT being something like the difference between B and some value that you need to subtract from B because there is the possibility of a default. So if there is no default possible, of course, then BT would be the same as the discounted value of B, right? And you see what we do here is we subtract something from it, which is B minus VT positive part. And exactly if this quantity is positive, there will be a default. So this means what we do is we decompose the part you get if there's no default and the part that is indicating a default. So this means we subtract some value from B, and this value corresponds to the value of a default, so to say. This is called a credit valuation adjustment. We talk about this in one of the later lectures. So this is very important. So this is not the discounted value of B, right? This is only true if a default is impossible. Otherwise, you really, I mean, this is what you have seen earlier. We need to adjust the structure here and subtract this kind of put option. And the put option is exactly indicating that there can be a default. Good. Next, we can look at the default probability. in this model. So default probability corresponds exactly to the probability of the asset value not being large enough to cover the depth, right? And this exactly means that we are in scenario 2 that you have seen earlier, that Vt is smaller or equal than B. Now we have the nice situation. All we need to do is to compute the probability of this, and Vt is something very nice. Vt is a geometric Brownian motion. So if Vt is modeled by a geometric Brownian motion, we have an explicit formula for Vt. Vt is, I can just show the formula again, but you have seen this already a couple of times, right? So Vt is exactly what is standing here, and then you just need to solve the probability of this being smaller or equal than B. So also this very calculation you have seen already a couple of times. So then you solve for the standard Brownian motion, relate this to the CDF of a standard normal distribution, and this is what you get on the right-hand side. Right? And this is under P, and if we do the same calculation under Q, then we get exactly what is standing here on the right-hand side. So all you need to do to come from the top line here, where things are calculated under P, to the calculation under Q is to, I just marked this, right, to replace the drift with the interest rate. Because this is the only thing more or less that changes in the stochastic differential equation. When you switch from P to Q, you just need to replace the drift, right? Okay, this is the probability of a default. First, the PD under P and the PD under Q. So we've talked about the differences in the last lecture. So one is the risk-neutral default probability, and one is the physical default probability. Okay. And this quantity here, yeah, you can also relate this to the D2 quantity that we have seen in the definition of the Black-Scholes price. Okay, so just one thing before we continue. I want to ask you just some basic understanding question. So look at this evolution. I hope this is large enough to see what is going on. So the blue line is indicating the asset value. The green line is the value of that, so the B. And the orange line corresponds to the value of that, so BT. So there's a difference between BT and B. And the question would be, so you see at some point the asset value is crossing the green line and so on. So if we have this scenario, maturity being 1 year, whether there is a default or not, in this very model, in the Merton model. Oh, I need to activate, sorry. As always. So now you can vote. Okay, so this is almost 50-50. Apparently a good question. Happy about this. Okay, so let's talk about the solution. So actually, in this situation, so this is the one we are talking about, there's no default. And the reason is, I mean, here we are crossing at some point. This is probably what has confused a couple of you. So here we are crossing actually that value. So this means the assets are smaller than the nominal. However, that doesn't matter, right? Because all that matters in the Merton model, so not in reality, but in the Merton model, is whether we are able to pay back the debt at maturity. So what we are looking at really is, so 1 is corresponding to t, right? So what happens at maturity, and at maturity the asset value is much larger than the debt value. So this means here what we have is really that V capital T is larger than B. And this means there is no default. It doesn't matter whether what happens in the meantime, whether Vt at some point is smaller than B. This does not indicate a default. Okay, and the second scenario is exactly the scenario of the default. Here you see that at some point, I mean, similar as before, we are crossing, the blue line is crossing the green line. This just means that asset values from this point on are smaller than the debt value, and what we have at maturity is that Vt is smaller than B. This means, in consequence, debt holders take over the ownership of the company, and in consequence, Bt will be Vt. So this means this is also what you see here, right? So the orange line is corresponding to the value of the debt, and at some point it's very close to the blue asset value. And in the end, we have that really that Vt is the same as Bt. This is not the case in the first scenario. In the first scenario, we have that Bt corresponds to B. Right? It's the same. In the first scenario, all debt is being paid back. So this means Bt is B. In the second scenario, Bt is smaller than B. Bt corresponds to Vt. Yeah, and this is again because the difference between the green line and the orange line corresponds to the value of a put option. A put option becomes larger the smaller the asset value is, right? And this means simply that the smaller the asset value, the more likely it becomes that the put option is being exercised, and the difference between the blue line and the orange line is becoming smaller and smaller. This is what we see here. Okay, and yeah, let's do a short break at this point. Okay, let's slowly continue. So we are in the Merton model. We have seen that all that matters is actually what happens at maturity, right? There are two cases. Either there is a default or there's no default. And the case of no default corresponds to the case that our asset value, VT, is large enough. So large enough means larger than B, so that we are able to pay back our debt. In the second case, there will be default, meaning simply that our asset value is not large enough, smaller than B. And in that case, debt holders receive just what is left, which is the asset value, so VT being BT, but equity value being 0. Okay, so we are in this model, and now we are thinking about the lecture last week, and in a lecture last week we have seen that one important quantity in credit risk is the spread. Just repeating the idea, which is that without any default risk, what you would do is to compute the value of a zero coupon bond simply by discounting the nominal value, right? E to the power minus RT. This is no more correct if there can be a default. The value needs to be smaller, right? So this means because there can be a default, so it's more risky, the value needs to be smaller. So this is there's some market premium for credit risk. And this means mathematically, of course, what you need to do is we need to discount with a larger value than only with R. And exactly this additional quantity that you need to add to the risk-free rate is called a spread. Okay, BT, therefore, which is the value of the debt at time small t, can either be written as we have seen it before, as the value of B minus a put option, which can be priced explicitly in the Black-Scholes model, or we can also understand this as e to the power minus R plus S times the time to maturity times B, right? So this is the formula from the last lecture, just telling you, okay, you can discount with the R plus S, which is the credit risky discount factor. And this means on the left-hand side, we have the price that was computed on the, before the break, which is the price of BT using Black-Scholes formula for a put option. This is what you get here on the left-hand side. So this is, more or less Black-Scholes formula. Black-Scholes for put option, so for B minus put option, and this is the value you get. And the right-hand side is exactly the definition of the credit spread. And then all you can do is you can multiply with the E factor on the right-hand side, take the logarithm, solve for S, and then what you get is exactly what is standing here. So you get an explicit formula for the credit spread. Okay, and this is just from equating actually these two quantities. There's no fancy calculation involved. It's just equating those two quantities which need to be the same by definition. And credit spread, again, the idea is really that if you look at things mathematically, so this is the formula we have, e to the power minus R plus S. So we have this additional S factor. And this is some kind of compensation. So you get an additional, you can also understand this as the yield. So you get an additional component in the yield. So you get a larger return for your money you invest. This means this pushes the price of the zero coupon bond down. It makes the bond cheaper for you if you invest. You get a larger yield. And the larger the yield, the riskier the bond. Right? So this means the higher the spread, the higher the corresponding default probability. And in this case, everything is linked to assets and liabilities. Everything is directly implied from the structure we are finding in the model. This means from the relation between assets and liabilities. So the relation between assets and liabilities is directly implying the credit spread. This is what you see here, right? If you look at the right-hand side of the equation we have derived, things basically depend on what we see here, Vt over B. So this is something related to the leverage ratio. So this means how large your assets are in relation to the size of the debt. Or if you like a more illustrative point of view, so Vt over B is the difference between the blue and the green line. I mean, this is more or less clear, right? So the larger the distance between the blue and the green line, the smaller the probability of a default. Right? The less you are leveraged, this is what it means, the smaller your debts are in relation to your asset values. And this corresponds to a smaller probability of default. This corresponds to a smaller credit spread. And this is what is formalized here on the right-hand side mathematically. Okay, so this is related to the leverage ratio. So this is a debt over asset value, debt over asset value ratio. So formally what you do is so leverage ratio, we use this in a second explicitly. This corresponds to B, and here we take the discounted value divided by Vt. So again, this is a ratio between the size of the debt, and you discount it, and Vt, so indicating how large your liabilities are with respect to the size of the overall balance sheet. So this means if the leverage ratio is very high, this means, again, think of the balance sheet. So here we have assets, here we have equity, and here we have liabilities. So on the right-hand side, let's say the liabilities are 90% of the overall size of the balance sheet. And this number can be inferred directly from the leverage ratio. This is exactly what it means. So the size of the liabilities compared to the overall size of the balance sheet. So how much you are bloating up your balance sheet by taking new debt. And the higher the leverage ratio, this means actually, the closer the green line in a relative sense to the blue line, the more likely a default. Okay, good. And now we come to the next question. So we have understood, hopefully, the credit spread and leverage ratio. And now we want to think about the credit spread. Okay, this one I also need to activate first. Now it's activated. So how does the credit spread relate to the volatility of the assets? So for this, you need to think of what the credit spread actually is meaning. So the credit spread is some measure that is positively related to the probability of default. And so what you need to understand to answer this question is how the probability of default is related to the volatility of assets. And maybe take a second, think about it, and think about the extreme case. So what happens if the volatility is 0? And what happens if you increase the volatility then? Okay. Now this seems to be, I was not expecting this, seems to be an easier question than the first one. Okay, I take this. Okay, we come to the solution. So comparing actually the answer to the question is comparing the different colors of the lines. So the green line is the larger volatility, orange is a bit smaller, and blue is the small volatility one. And so what we see is that the higher the volatility, the higher the credit spread. And also what we see is that the higher the leverage ratio, the higher the corresponding credit spread. I mean, this makes sense. Again, credit spread corresponds to default probability. So this is a compensation for a higher default probability. And leverage ratio is something I explained. The higher the leverage ratio, the closer the two lines, so the more likely a default. And Y is a higher volatility corresponding to a higher probability of a default. Again, I would really start with the extreme case. If there's no volatility, this just means there's no possible scenario where you can default. Right? You start always above. You're not starting in default, right? So this means in the beginning, the blue line is larger than the green line. If there's no volatility, there is no possible scenario where you can default. If you slightly increase the volatility, I mean, there's still a small probability that you can default, and the larger the volatility becomes, the more possible scenarios in which the blue line can be at the end below the green line, right? This happens when you increase the volatility. But this means, therefore, the higher the volatility, the higher the probability of default, and therefore the higher the credit spread. This is exactly what we see here. So we see two things: volatility dependence and leverage ratio dependence. Okay, and then we compare the leverage ratios in a bit more detail. So there are, here in this case, three different cases. So in the first case, the leverage ratio is very small. And then there's some medium leverage scenario, this is the orange line, and some high leverage scenario, the green line. And then we look at different maturities. So we let things depend on maturity. And we see that with an increasing maturity, the three lines, first of all, the three lines converge to each other. So this means for very long maturity, it actually doesn't matter whether you are initially highly leveraged or not highly leveraged. It's the first observation. And we also observe that for the highly leveraged case, the line is decreasing. This means for a very short maturity, the default probability is actually quite high. But if time increases, you have enough time to recover. There's typically a positive drift, and then you end up in more scenarios where you are not in default in the end. So this is roughly the explanation for this picture. This is just written down here in more detail. So for a low leverage scenario, it just means in the beginning the assets are sufficient to cover short-term liabilities. So this means there is little probability for default and therefore a very small spread in the beginning. Okay, and then, I mean, it can be that if maturity increases, there are additional scenarios where you can default in the end. For medium leverage, we also start with very small spreads, and then additional fluctuations come in for highly leveraged scenarios. Again, if more time passes, assets typically grow larger, less scenarios lead to a default in the end. And also, we see this convergence of all of the three cases in the end. They just tend in the long run to the default probability with t going to infinity. Good. So this is the Merton model in a nutshell, and now we want to come to a practical application of the model. So, and to this end, we need to. We have a model. The model involves parameters, so we need to be able to somehow determine them. This includes the maturity, the size of the debt, the asset value. So the asset value is not a trivial quantity because typically we can observe the equity value but not the asset value. And same for the volatility, right? We can observe maybe or estimate the equity volatility but not necessarily the asset volatility. Okay, and because we can only, I mean, here I write observe, but observed is maybe too much, right? I would say estimated. I mean, this is typically a latent quantity, volatility. You cannot directly observe them, but you can observe the, you observe the equity values, and based on the equity values, you can define reasonable estimators for the volatility. Okay, but not for the asset volatility, because you cannot directly observe asset values, how they evolve over time. Okay, and what we can do, however, is we can derive, based on the equity volatility, a relation for the asset volatility, which is written down here. Okay, and why is that? This is because we have that, so maybe I need to start writing here. ST, equity value, can be understood as the value of a call option on the asset value. So this means, this is what you have seen earlier, so this is the risk-neutral value, risk-neutral discounted value, expected value of the call option value, call option payoff, so VT minus B positive part. And this is the Black-Scholes price, so call option price, Black-Scholes, CBS, depending on, and here I should be a bit more precise. This is actually, if I'm talking about the value at time small t, conditional on ft, and this depends only on the value vt. So this is a value CBS that depends on vt and t. Okay, CBS just means Black-Scholes formula for a call option. Okay, so this is what we have seen, and now what we simply assume here is that the equity value, I mean, this is the same assumption we have already imposed in QF5203, follows also a geometric Brownian motion. So this means dst would be mu s st dt plus sigma s st dwt. Black-Scholes model, actually, for the stock value. And we also have this relation that st is the Black-Scholes price of vt. This means what I also can do is I can apply Ito's lemma to the above equation. So this means I have here partial derivative of s, which is the Black-Scholes value with respect to v dvt, plus second order term, be the second derivative with respect to v, then the quadratic variation dvt squared plus ds dt dt. Okay, it's just applying Ito here. It's Ito. And I'm just using the GBM assumption for Vt. This means I have here ds dv, which is the delta term. Right? It's just a derivative of the call option with respect to the underlying value, which is delta. The second order term is the gamma term. The dt term is related to the theta. So we have here ds dv mu v vt dt plus ds dv sigma v vt dwt then 1/2 second order term dv squared. dvt squared would be just sigma v squared vt squared dt plus ds dt dt. Okay, now you have a lot of dt terms and one dwt term. Now what you do is you simply compare the coefficients. So you have two representations for dst, and you have one time this coefficient of dwt, and using Ito's lemma, you get this coefficient of dwt. They need to be the same. So this means, in consequence, you get exactly this equation here. This is just from applying Ito's lemma. Okay, and this means we can relate the sigma s to sigma v. And now the nice thing is that, again, you see that we have assumed that geometric Brownian motion was really a good choice because this allows us to compute the quantities. We can compute, for example, this derivative, ds dv, because, again, s is the price of a call option, and therefore ds dv just corresponds to the delta, the derivative of a call option with respect to the underlying value, which can be computed explicitly in the case of a geometric Brownian motion, which is just this CDF of a normal distribution evaluated at dt1. This means we can replace the partial derivative on the right-hand side with this quantity n of dt1. And then what we get is an explicit formula for sigma v, the quantity we cannot estimate directly in relation to sigma s, which we can estimate based on values of the stock that we observe and the quantities involved on the right-hand side. Okay, and this is true for all the t's, and we just do this at initial time 0. Good. Okay, and then we continue with the parameter estimation. So this is one way, so the relation you have seen here is one way to get some estimation for sigma s, but this doesn't necessarily explain how to get the other parameters that are involved. And to this end, so there are a couple of possibilities how to do this, and one of the, nicest approaches actually is the so-called Hall-Nelken-White approach. And what you do in this approach is you use option data, option prices you observe on the financial market. And all you need to do, you need to be able to observe at least 2 put options written on the corresponding equity value. So the assumption is here that really that the company, is traded on exchange, and you are able to, and there are options traded on this company. And in that case, you can apply this approach. So if there are no options traded on the company, of course, you cannot apply this approach. But if you have a big company, let's say, and it's exchange traded, and there are options publicly available, and so on, then you can apply this approach. And then the assumption is not a very, very strict assumption that there are at least 2 put options on the company. Okay, notation here would be psi j, so j being 1 or 2, and the corresponding strikes are k j. Good, and the maturities are earlier than the maturity of the bond, so tj corresponding to the maturities of the put options are smaller than t. And then, using this assumption leads consequently, without without computing a lot directly to these two equations we have here. So the first equation, S0, being what is standing on the right-hand side, is just relating, again, the value of S0 to the value of a call option. So again, equity value is assumed to be a call option written on the asset value. So therefore, we have what is standing in the first line. And the second line is just saying, okay, psi j are the things we observe on the market. So the values, the prices of the put options, and the right-hand side is what we compute as a price in the model. The model is assuming that Vt is a geometric Brownian motion, St is a call option on the geometric Brownian motion. So what is standing here on the right-hand side is a put option on a call option. And this is called a compound option. So again, the idea would be this is a put option, just a put option, not a compound option. But because in our model we assume that our equity value itself is a call option, what we have mathematically is a compound option we need to evaluate here. And the nice thing is, in the Black-Scholes case, geometric Brownian motion case, all these quantities can be computed, right? So this is, again, one very nice feature of geometric Brownian motions. You're simply able to compute more or less everything, right? So that's one of the attractions of this model, and that's why you can use this approach. Okay, to summarize what we have. So on the left-hand side, we have all the quantities that are that you can observe in the market. So these are observables, right? So we have S0, which is today's stock price, psi j. These are the prices of the put options. So there's nothing to compute. And the right-hand side is involving the quantities you want to compute. So this is involving, in particular, 3 unknowns. This is involving B. This is involving V0, so the initial value of the assets. You don't know this explicitly. And sigma V. So it's just a nonlinear equation on the right-hand side involving 3 unknowns, and you have 3 equations, so you can solve this explicitly. Not using linear algebra, but there are numerical methods to solve this equation. Okay, and then there's I just do this very fast. There are formulas to compute the value of a compound option. I don't know if this is covered in other lectures and so on. I just give you the formula, so this is roughly how it looks like. Again, this is, in this case, a put option on a call option, and this is how the corresponding value looks like. So N2 in this case corresponds to the CDF of a 2-dimensional normal distribution, and here you see the corresponding values. This is the variance parameter, and there are just some parameters being specified. And in the end, all you need to do is just to, as always in the Black-Scholes model, right, to evaluate this integral, do some fancy manipulations of the integral, and then if you evaluate this, you get this formula. Okay, I don't want to specify the details. The formula is here. It's just telling you the message, conveying the message here that you have 3 equations. They can be solved explicitly. If you plug this into Python, run the corresponding solver, you get the solution for the system of equations. Okay, I'll just illustrate this with an example. If we have a company whose stock price, so equity value, is $100, and we assume that the maturity is 5 years, so this is one common assumption for this approach. Then we want to apply this approach, so this Hull-White-Melken approach. This means to this end we need to observe 2 put options. The first put option has maturity 1 year, so smaller than 5 years. Strike price 95, and the price of it is quoted in implied volatility being 40%, so you can apply the Black-Scholes formula to convert this to a price. The second put option, also a smaller maturity than 5 years. Assumption is fulfilled. Strike price being 90, implied volatility being 25%. Again, you can convert this to a price. So you have 2 prices of put options. Additionally, you observe the equity value. This determines the left-hand side of the system of equation. And then you can compute the right-hand side and solve it for the quantities you want to solve for. Okay, in the first step, we need to explicitly convert the implied volatilities, sigma 1 and sigma 2, to prices. So we have psi 1. Again, what you would do is you just have the Black-Scholes formula for put option. And then you just enter this implied volatility of 40%, and then you see what the corresponding price is. This is all you need to do, and you get 12.11 for the first option and 10.81 for the second option. Well, we assume some interest rate, 2%, and then I mean, there's nothing to explain here. You just let the computer solve this system of equation, and then what you get is corresponding values for B, sigma V, and V0. This is actually a very nice approach because it's directly market implied, and you don't need to impose a lot of things. You just need to solve these systems of equations. And then you can work with this. Now you have specified all the parameters in the model, and you can explicitly compute quantities like the credit spread, for example. The credit spread, so the formula I'm applying here is exactly the one you have derived here. So just where we equate the quantity for BT, which is the difference between B and the put option, and the quantity with the spread. So this was leading to this equation for the spread. And if we now use this formula for the spread in this setting where all the parameters are being specified, we get an explicit spread of 0.7% roughly. Okay. So the next thing, so you see this is a very nice model, right? You can really compute things. So I like this very much, just from assuming a certain structure between equity and assets, actually. For example, also the expected loss as a quantity you can compute very nicely here. And the main idea here is to compute the expected loss as the difference between the risk-free bond, the value of a risk-free bond, and a risky bond. Okay, and this is probably something I mean, we will do this again and again, and this is something I need to explain why this is reasonable. So the expected loss, maybe I just start differently. I start with what I want to show. So I want to show that you can really relate the expected loss to the difference of these two values. So I just look at the difference between these two values. Okay, let's do this. So I have the difference between the value of a risk-free bond, which is just a discounted value of the nominal value. So this is the value of a risk-free bond. And the value of a risky bond would be what? It would be for this I need to apply the expected value operator. It would be the discounted value of what you get in the case of a default. In the case of a default, you get some recovery rate times the nominal value, which is B. And this is true in the case of a default. And in the case of no default, you just get the whole nominal back, so B. And I need to multiply this with the indicator of no default. Okay, so this is the difference between the value of a risk-free bond and a risky bond. And now I just simplify. So, I mean, all the quantities are being multiplied with the same discount factor. So I can write this in front of everything. So I have e to the power minus r times t minus t times. And here I have b. I can also write this in the expected value operator if I want to. So I have expected value of b minus, and here I have r times b, indicating a default. Okay, and here I have an indicator function which is indicating no default. So this is just 1 minus indicator function of a default. Okay, it's just simplifying things a bit. And I mean, the only quantity here which I want to assume that to be stochastic is the indicator function. Right? I can assume the recovery rate to be deterministic and so on, just to illustrate the principle. And the expected value of the indicator function is what? It's just PD. The expected value of 1 being default is exactly corresponding to the probability of a default, PD. So if I compute this expected value, what I get is e to the power minus rt minus t times. Now I have b minus r, b, r, maybe I just should indicate the dots, r times b times PD minus b plus b times PD. Okay. And now what we have is, you see the b cancels out. And I end up with the same as the discounted value of b times PD minus r times b times PD. So I have something like 1 minus r times b times PD. And it's the same as the discounted value of, 1 minus r is just loss given default. B is the exposure at default, and PD is PD. So this means what we have here is really the expected loss. Okay, so the the discounted value of expected loss corresponds exactly to the difference between the value of a risk-free bond and the risky bond. This is just what you see here. Okay, so this is where I start here. So again, the discounted value of EL corresponds to the difference between the two values. This is the value of a risk-free bond, risk-free, and this is risky. And this corresponds to BT, so the value BT that we have derived earlier, where we, just consider the value of B minus the put option. Okay, and then if you simplify this, you get this equation here, just by applying again that n of dt2 is 1 minus dt n minus n of minus dt2. So this is what you see here. You can simplify this again, and then the first discounted B cancels out, and you get this equation. Okay, and then you have this equation. You can multiply with e to the power r t minus t, and you get an explicit equation for EL, which is standing here. This is very nice. In particular, because we know that the expected loss can be written as default probability times exposure at default times expected loss given default. And we know this corresponds to the PD. Right? The first factor corresponds to the PD. So this means the second factor needs to correspond to the exposure at default times expected loss given default. But we know what the exposure at default is, which is this is exactly B. So this means, on the other hand, that the expected loss given default is explicitly known from this quantity. I just need to divide by B. So this would be 1 minus e to the power r t minus t times vt times this ratio between n minus dt1, n minus dt2 divided by b. Yeah. Okay. Yeah, so again, this is a very nice model, but on the other hand, we need to live with the assumptions we need to make. So this means, in particular, one of the drawbacks is that we are working with the asset value, with the firm value. And this is, unfortunately, a quantity that we typically cannot observe directly in the market. On the other hand, what we typically, to bypass this drawback is that we somehow use the equity value in order to estimate values for the asset value. In the Hull approach, you have seen this, right? Put options on equity, or when we apply Ito's lemma as well. So you somehow want to use that the equity value is observable and so on. But this is only possible if the stock value is observable. This means if there are stocks traded. Otherwise, of course, this cannot be used. And there are very important examples. Governments don't issue stocks, for example. So you could not determine the PD for a state using this approach. Okay, and the model is just assuming one period. We model everything in between in a continuous way, but still, we are only looking at the maturity, what happens at the maturity. So this is a static model. We also assume that nothing happens in between concerning the capital structure of the company. So the capital structure of the company is completely fixed. This is really a restrictive assumption because this is typically not the case. You can extend this to a certain extent, but this makes the model much more complicated. And also, you need to be aware, we are working with a geometric Brownian motion. Again, I've mentioned this has the big advantage that you are able to compute things, but the drawback is that you need to impose the assumptions of a geometric Brownian motion. In particular, the returns are normally distributed. And this just means that you are severely underestimating tail events. Extreme events are completely underestimated. And these are actually the events you are looking at, you want to compute, right? So these are really drawbacks you need to be aware of. Okay, nevertheless, let's look at a couple of exercises, just illustrating how the model can be used. If we have a company that has initial assets with a value of $100 and the asset volatility is 20%. So asset volatility means this corresponds to sigma V, and $100 corresponds to V0. Risk-free rate is 10%. Time horizon 1 year. Leverage ratio, and same definition as before. So B to the power, just discount value of B. In this case, the discount is very simple because capital T is 1 year, so it's just b times e to the power minus r divided by v0. This is the leverage ratio. This should be 90%. Okay, then we want to compute the things we can compute in this model. So the first thing would be the credit spread. The second would be the default probability, and then the expected loss. Okay, for the credit spread, we need to think a bit how we can do that. So, I mean, if you look at this equation, right, the leverage ratio being 90%, then you can, so what you want to do is you want to use exactly this relation in order to determine the size of B. That's the first step. And then you want to look at the value of BT, and the relation between B and BT tells you exactly what the spread is. So that's the line of working we have in mind in order to compute the spread. Okay, so leverage ratio of 90% means exactly what I have written down, right? So this is exactly this relation. So how much, how many debts we have in comparison to the size of the overall assets. So how bloated our balance sheet actually is. Okay, and then we can solve this, and we see that, I mean, V0 is known, right? V0 is exactly this value 100. So this means we can solve this for B by just multiplying the right-hand side with 100 and everything multiplying with e to the power 0.1, and then we get a value of B as 99.46. Okay, so we know the size of the debt, and then in the next step, we can compute the equity value. Why do we want to compute the equity value? Because the equity value also tells us the value of the debt. I could also compute BT. This would tell me the same thing, right? Because I know that V0 is the same as S0 plus B0. When I know V0, I can just compute one of the quantities on the right-hand side, and then I know the other quantities. So I can compute S0 using Black-Scholes formula for a call option, and this is what I get here. This would be $13.59. Then I can, using the structural equation, balance sheet equation, I can compute the value of the bond at initial time without applying the put option formula, just from using V0 minus S0. 100 minus the value of the call option, and this is $86.41. And then I can compute the yield. So I know that B0 can be computed in two ways. Right? This is what I explained earlier. So either you apply the explicit equation you get in the Merton model, which is to compute the value of B minus the value of a put option, or you just say, okay, B0 can also be used, can be computed using the spread or the yield. So you can also write something like e to the power minus yield times maturity times B, or the same as e to the power minus R plus S times T times B. Right? So all of this is okay. And if we solve this equation for y, for the yield, then we get this the same as the logarithm of B over B0. We have computed B and B0, and we get a yield of 14.07%, and the yield is the same as R plus S. R is the interest rate, 10%. So this means if we subtract the interest rate from the yield, we get exactly the spread, which is 4% in this case. Okay, so what we did was we had initially this equation in mind, and then we were just solving for B0 using the quantities we had. Okay, and then, I mean, everything I need to know to compute the other quantities is there. I just can apply the formula for the PD. PD can be computed as, this is the probability of Vt being smaller or equal than B, which is exactly n of minus D2 or 1 minus n of D2. You just enter the formula and you get a default probability, which is quite high, more than 1/3. And the expected loss, using the formula from the previous slide, you can directly compute. So it's default probability times, what you have here, which is exposure at default times expected loss given default, and you get an expected loss of almost $4. The second exercise would be a bit similar, but using other tricks we have seen. So the setting is the following, that the same initial price, it's just toy values, doesn't matter. Okay, and then we have 1 year debt with value $200. So you see there's quite some difference between the equity value and the debt value. And so what we have here is the stock price volatility. So what we observe is that sigma s has a value of 40%. So we observe sigma s. This is the situation in practice. You don't observe sigma v, but you observe sigma s. This would be 40%. No dividends and so on, right? And risk-free rate 3%. And then you want to compute things. So in particular, you can typically not observe the asset value. You cannot observe the asset volatility, as I've explained. You can only observe the quantities which are here: equity value, equity volatility, and now you want to infer the other quantities using that. And also like the value of the bond and the default probability. Okay. So because we don't observe any put option prices here, no compound option pricing formula applicable here or nothing like that, the only thing we can do really is to apply Ito's lemma, the equation that we got from Ito's lemma. So this is the equation you see here, the second equation in the second line. So 0.4, which is the corresponding value for sigma s. And the right-hand side is the equation from Ito's lemma involving sigma v and also v0. And the first equation, 100, is exactly the initial stock price. And we know the structural equation, right? We know that the S0 is a call option on the asset value. And therefore, it corresponds to the price of that can be computed in the Black-Scholes model, which is standing on the right-hand side. And now we have two equations with two unknowns, which are sigma v and v0. And then you can solve it, right? No worries. I cannot give you this in an exam or something like that, because, this involves really numerical methods that are not in your pocket calculator, probably. But, if you enter this into Python or something, you get the numerical solution for this. You get sigma v and v0. And in this case, v0 would be 294, and sigma v would be 13.6. And then you can also compute the other things, the value of a zero-coupon bond. If all the parameters are specified in the Merton model, this just corresponds to the computing the value of a put option in the Black-Scholes model. You have the formula, and then you get 194.08. You could also get this from, you have S0 and V0, right? S0 is 100, so you could also just subtract 100 from this quantity. This is the same thing. So B0, just V0 minus S0. And then you can also compute, whatever you want. For example, the risk control default probability of the company, which is quite small, simply because there is, there's quite some substantial difference between V0 and B0. Okay. Yeah, Okay, I think I will just finish today without a second break because, I mean, what is left is just like 10 minutes, not more. So this is all about the Merton model. So it's, again, this is a very nice theoretical framework to compute things and so on. But you see there are a couple of assumptions that need to be imposed in order to apply things in practice. So typically, the Merton model is not used directly in practice. So in industry, there's an alternative that is called the KMV model that is based on the Merton model. So it's more or less assuming the structure, the nice quantities you get in the Merton model, but it's a bit more tailored to the needs of companies in industry. Okay, so what is the KMV model? So the KMV model, so this is a vendor model. So this means there's a company that has thought of this model, that had the idea of making up some model based on the Merton model and to sell it to other companies. And the founders are, I mean, they have the name Kielhofer, McQuown, and Vasicek. Therefore, it's KMV. And then after some time, they sold it, and now it's maintained by Moody's, so one of the big rating agencies. So that's roughly the history of the model of the company. And yeah, so they have actually the idea is that they have a huge database of companies, so of historical data of companies, of the balance sheet, of the structure of the company, and whether they have defaulted or not. And they use this data in order to get some model that is actually applicable, from which you get actual PDs. Okay, and the basic idea is based on what you have seen before. So it's based on the Merton model. So this means we assume the same underlying structure, the same underlying idea. So in particular, equity is the call option on assets. Okay, and the contribution really is not the theory because you will see later, it's in some parts, it's just a simplification of the Merton model, but not like an expansion that makes really theoretical sense, but it's really just, you take the Merton model, simplifying it and tailoring it so that you can really get even simpler formulas that you can apply in practice. Okay, and the main contribution, therefore, is not the theory, but really like having a model that fits the huge database they have. So they are selling more or less the data they are using. Okay, and the contribution, therefore, is the calibration to the database they are providing. Okay, and then the main quantity now in this model, KMV, so I need to introduce another abbreviation, is called EDF. So this stands for expected default frequency. You will see the definition in a second. And this is what defines how likely a default is. So this corresponds more or less to the, so it's not exactly a PD. It's not exactly a default probability because you lose a bit the interpretation of the model because there are so many simplifications. But this should be the quantity you have in mind. It corresponds roughly to the probability of a default. And this, it should not surprise you, right? Because it's based on the Merton model. This depends on the capital structure. So this you compare really the equity size with the liability size and so on. So the leverage ratio plays a role. So the whole capital structure, the size of the debt, and all these quantities that also influence the PDs in the Merton model, they are also important for the KMV model. Then I mean, yeah, it's the same idea as in the Merton model. So the volatility of the asset returns, the higher the volatilities, the more likely a default becomes, and so on. And also today's asset value. We talk about the calibration of these values in a second. Okay, the EDF actually just corresponds conceptually to the PD in the Merton model. So, but it's not the same thing, but it's the starting point for defining the EDF. So the starting point is exactly this quantity. So we have the PD in the Merton model, and you have seen the right-hand side. This is the probability of Vt being smaller or equal than B, 1 minus n of D2, so to say, but under P, not under Q, because you have the historical measure P, because you want to calibrate according to historical data. And now you're taking this quantity and you're simplifying it a bit. So what we have in the Merton model is 1 minus n of some argument, right? So, and 1 minus n is the CDF of a standard normal distribution. This is a decreasing function, because n is an increasing function. And this function, 1 minus n, is now being replaced by something else. And the something else is just something that fits better the data they have, right? There's no theoretical backing for what they do. You just replace it by some other decreasing function. So therefore, you lose a bit the meaning of a default probability. So therefore, they call it expected default frequency, right? Okay, so that's just some ad hoc practical approach. So you replace the 1 minus n by some other decreasing function based on empirical estimation based on their database. The next tweak they apply is to replace the b, so the size of the dat, by something that is taking into account also the maturity of the dat. Because this is one drawback of the Merton model, right? You only have a fixed maturity. So therefore, if you have more than one dat with different maturity times, you cannot appropriately take this into account. So therefore, what they do, again, pretty ad hoc, right? They just say, okay, 100% of 1 year liabilities plus 50% of maturity of liabilities with a longer maturity than 1 year. Just somehow respecting that, liabilities with different maturities have a different influence on default probabilities. Okay, and then the next step, third step, would be even to look at this argument that is the input to 1 minus n in the Merton model, and to simplify this further. For example, to say that you have here the difference between mu and 1/2 sigma. This typically both are small quantities. The drift is small, volatility squared is small, and also they are close to each other typically. So they just ignore this term, so to say. The second would be to replace the log return just by returns, actually. Okay, I'll talk about this in a second, but first, before I come to the simplification, I want to explain how we actually get the other quantities in the input, right? So there's V0 and sigma V, and according to what I explained earlier in the Merton model already, the estimation of these quantities is a problem, right? You cannot observe them. You need to get them somehow from the data you have. And what they do in the KMV model roughly is to apply some iteration procedure to get the asset value and the corresponding volatility. So here it's standing on a high level, but to be a bit more precise, so this is just some iteration, let's say. And the iteration is doing the following. So you start with some initial value sigma v. So initial value sigma v, let's call it sigma v1. And then you have data, or let's say stock prices, to be a bit more precise. So equity values, stock prices, ST1 to STN. So just some historical stock data. And now you know that in the Merton model, STI is the value of a call option, and the value of the call option on the asset value, depending also on the underlying volatility. So this is the call option price in the Black-Scholes model, depending on the asset value, VTI, and also depending on the assumed volatility. So you're just taking the initial value you have assumed. And now you have this equation for ST1 to STN. Right? And now you're solving just for the corresponding VTIs that make this equation match. So you're getting VT1 to VTN. So something like a historical time series of asset values. And then you have this time series of VTIs, and then you can estimate sigma V, now we call it sigma V2. And then you repeat and repeat. So this means you would repeat all of these steps. And this converges, you can show this and so on, and then in the end you get some asset values, VTI, and also the corresponding volatility. So this is roughly the idea, how the parameters are estimated in the KMV model. This means you have the sigma V, you have the V0, and then you're coming back to the simplification of the argument. So this is the original argument you have here. Again, you assume that this should be 0. Just a simplification, very, very ad hoc brute force approach. So this means you are left with the log return, or log V0 over B. And now what you do with this argument is logarithm of V0 over B is the same as the difference between log of V0 and, here you have B tilde because you replace B with B tilde, right? And you can just apply a first order theta approximation in order to get that this is more or less the same as the V0 minus B tilde over V0. So probably you have seen this already. I think I was also explaining this in one of the earlier lectures of risk management. So this is just a first order approximation, first order theta approximation. And then you get something that is called a distance to default, DD, which is actually the argument you input into this decreasing function. And this corresponds to, just some approximation, some simplification of the argument you give into the normal CDF of this DT2. Okay, and then the question that is left is more or less how to get this decreasing function. This is just based again on this database. So for this estimation, so it's not like they publish a formula, right? It's a vendor model. So you input the parameters and they give you the PDs, right? So they don't publish the formula or something like that. But on a high level, what is being done, how they sell the model is that they in their database they consider similar companies to have a similar default probability in the end. So this means they consider companies of a similar structure. So this means having the same input parameters, having the same PD. So this requires them to map similar companies to the same probability of default. This means they are assumed to be homogeneous in these quantities and default probabilities for equal distance to default. This is the assumption, and this is just being done empirically. So they just estimate somehow this function based on historical default events. So this means you have as an input the corresponding quantities that influence the probability of default, something like the size of the debt, the corresponding equity value, and so on. And then you know how, I mean, you have the historical database, and you can look this up, how companies of this structure, how often they have defaulted in the past. This gives you some estimation for the default probability of company with the structure, and based on this, the corresponding mapping is being estimated. And they just take something like the average EDF. So you have different quantities, different default probabilities, and then you average over them, and you get some default probability that corresponds. I mean, they don't call it probability of default, but again, it's the EDF, but you should think of that as a probability of default. Okay, and just to illustrate this in a very simple example, so you have, consider a company that has 100 million assets. You get this value from this iteration procedure in the KMV model. You have different liabilities. So short-term liabilities of size 50 million, long-term liabilities 60 million, and then a volatility 10%. Again, you would also get this from the iteration procedure. And then you can compute the distance to default. It's a very easy calculation, just involving those 4 quantities. You need to assign a factor of 0.5 to the long-term liabilities because they are something like less prone to default. This is called a default point if you consider this weighted sum. In this case, the distance to default would be 2 if you input the values, and then you plug this into the corresponding function. If you take 1 minus n, which you don't, in the case of KMV, because you replace this, but just as a proxy, we take 1 minus n, then you will get a default probability of what is standing here, 2.2%, and this corresponds then to the EDF. This is roughly how it is done in the KMV model. Okay, so yeah, a bit early today, so I'll stop here, and then we continue with the hazard rate models next time.